When we talk about PKI, we're really talking about a trust system with several specialized players, not a single magic box. At the core is a simple need. Systems, people, and devices must be able to prove I am who I claim to be, without already knowing each other. To make that work at scale, PKI splits responsibilities. Some components anchor trust, some issue identities, some verify who's allowed to get them, some publish the results, and others enforce the rules when something goes wrong. In this module, we'll walk through each of these roles and see how their interactions create a trust fabric for your organization's digital infrastructure. The root certificate authority is the master key of your entire trust system. Every other certificate in your PKI ultimately depends on this one key being trustworthy. It doesn't rely on any higher authority, it signs its own certificate, which is why we call it self-signed. Because everything chains back to it, the root's private key must be protected more than anything else. In a well-designed PKI, the root is kept offline, sometimes literally locked away and powered on only for rare, tightly controlled ceremonies to issue or renew intermediate CAs. It should never be used to sign end-user or server certificates directly. The logic is straightforward. If a normal certificate is compromised, you revoke it and contain the damage. If the root is compromised, the entire ecosystem's trust collapses. Strong isolation, strict procedures, and minimal use are therefore non-negotiable for root CAs. Intermediate certificate authorities are the workhorses of a PKI. Because the root key is so locked down and used so rarely, the root signs a small number of intermediates, and those intermediates handle almost all day-to-day activity. You can think of them as a protective layer in front of the root. If a root key is ever compromised, every device and certificate that trusts it is suddenly at risk, truly catastrophic. By inserting intermediates, you distribute trust. If an intermediate is compromised, only that branch of the hierarchy needs to be revoked and rebuilt. The root can stay offline and safe. Operationally, intermediates issue end-entity certificates to servers, devices, and users. They publish revocation information and answer status checks like OCSP. So when you browse to a secure website or connect a VPN, you're almost always relying on an intermediate CAA, quietly backed by a deeply protected root. As PKI grows inside an enterprise, relying on a single intermediate CA for everything becomes risky and hard to manage. A more robust approach is to create multiple intermediates, each specialized for a purpose. For example, one intermediate might issue certificates only for internal employee identities, another only for public web servers, and a third dedicated to high-security systems like finance. All of these intermediates ultimately chain back to the same root, but they're separated by type of use, geography, or organizational boundary. This segregation gives you strong blast radius control. If one intermediate is ever compromised or misissues certificates, you can revoke or distrust just that branch without taking the whole organization down. It also lets you fine-tune policy per area, stricter identity proofing and key requirements where the risk is highest, and more flexible rules where you need speed and scale. In PKI, the registration authority is the gatekeeper between people asking for certificates and the certificate authority that actually issues them. You can think of the CA as a very powerful but very blind machine. It can sign anything it's told to. The RA's job is to make sure it's told the right thing. When someone requests a certificate, the RA checks who they are, whether they really control this domain or system, and whether the organization behind it is legitimate. That might mean verifying government ID, confirming DNS ownership, or checking corporate registration records. Only after those checks pass does the RA approve the request and allow the CA to issue a certificate. This separation is crucial. Machines handle the cryptography, while the RA adds a human and organizational layer of trust. which is what ultimately makes a PKI-based identity believable. A PKE is useless if nobody can find or verify the certificates it issues. That's where certificate repositories come in. They're the public directories of your PKI world. Inside enterprises, directories like LDAP or internal web portals. Let applications and people look up certificates for users, devices, or services. That's how systems know which key to use when they want to talk securely to HR server, on the public internet, or to a particular employee. Transparency logs publish every issued certificate in an append-only, tamper-evident list. Security teams, domain owners, and even attackers can see what exists. That visibility makes it much harder for a rogue or misconfigured CA to sneak in a fake certificate without being noticed. End-user devices also depend on pre-installed trust stores in browsers or operating systems. These act like a curated address book of which certificate authorities are trusted in the first place. Together, these repositories enable three critical things: validating that a certificate is real and current, providing transparency so bad certificates can be spotted quickly, and supporting auditing so organizations can track their own certificate inventory and avoid nasty surprises. When a certificate should no longer be trusted, you can't just wait for it to expire. That's where certificate revocation lists, or CRLs, come in. A CRL is a digitally signed list of certificate serial numbers that the certificate authority has declared invalid. Think of it as a blacklist that other systems can download and check before trusting a certificate. Revocation happens for everyday reasons. A private key might be compromised, an employee leaves the company, a service is decommissioned, or a business shuts down. In all of those cases, you want existing certificates to stop working. CRLs are appealing because they're conceptually simple, very robust, and can even be used in offline or constrained environments. But they do have costs. The lists can get large, consuming bandwidth, and they're only updated periodically. That delay creates a security gap between the moment a certificate is revoked and the moment everyone has the latest list. Modern PKI designs still support CRLs, but increasingly combine them with more real-time mechanisms, like OCSP, to shrink that gap. OCSP is how a client asks, in real time, whether a specific certificate is still valid. Instead of downloading a big revocation list and searching through it, the client sends a quick question to an OCSP responder. Is this exact certificate okay? The responder replies with a signed answer: good, revoked, or unknown. You can compare CRLs to downloading the entire phone book, while OCSP is like calling directory assistance for one number. It's lighter, faster, and easier to keep current. To avoid a network call on every connection, we use OCSP stapling. The server periodically asks the OCSP responder for the status of its own certificate, then staples that signed status to the TLS handshake. The browser gets both the certificate and fresh revocation proof in one shot, which improves speed, and also reduces privacy leakage about which sites the user is visiting. OCSP responders are a classic example of delegated authority in PKI. The certificate authority focuses on issuing and revoking certificates, while responders focus on answering the question: is this certificate still valid right now? This separation brings three major benefits. First, scale. Validation traffic is huge. Browsers and services around the world can hit responders millions of times per day, without ever touching the core CA systems. Second, security. You want your CA as locked down and offline as possible. By pushing real-time status checks to responders, you keep the CA's signing keys out of the daily traffic path, which dramatically reduces exposure. Third, resilience. If a responder is compromised or misbehaves, you can revoke just the signing certificate used by that responder and spin up a new one. The main CA keys and trust anchor remain untouched. Delegated OCSP responders, in short, let you validate certificates at internet scale, without sacrificing the security of your most critical CA assets. Revocation is how you say this certificate is no longer trustworthy before it expires. In practice, you usually choose between CRLs and OCSP, and the right mix depends on your environment. OCSP provides real-time status checks. A client asks, "Is this single certificate still valid?" and gets a quick yes or no. That's ideal for public web traffic and modern applications where latency matters and you don't want to download large lists. CRLs are downloadable lists of many revoked certificates. They're heavier, but they shine in high security or partially offline environments. You can preload the list into an air-gapped network and still enforce revocation without live internet access. Most mature PKI deployments don't treat this as an either-or decision. They use OCSP for speed and user experience, and keep CRLs as a robust, auditable fallback when OCSP is unavailable or when offline operation is required. You can think of a complete PKI as an assembly line for digital trust. The process starts when someone or some system asks for a certificate. Before anything is issued, a registration function checks who this is and whether they're allowed to get this identity. That identity vetting is the first gate. Once the request is approved, the certificate authority actually creates and signs the certificate. Its private key is the root of trust. If that key is compromised, including this situation of Voidgate. Next, the newly created certificate is published somewhere that others can find it, typically a directory or repository. At the same time, status information is fed into revocation services, like OCSP or CRLs, so relying systems can see whether that certificate is still valid or has been revoked. When an end system connects, it doesn't just accept the certificate. It checks the chain up to a trusted route, and it checks status through those revocation mechanisms. Only if all of that looks good does it treat the connection as trusted. The key idea is system synergy. Every piece depends on the others. If identity verification is weak, issuance is sloppy, the repository is out of date, or revocation is broken, the trust chain fails, even if the cryptography itself is perfect. By now you know what each PKI component does. The next question is how we keep each one safe, so the whole trust model doesn't collapse. The root CA is treated like a crown jewel. It should be offline, locked in a secure facility with its private key inside an HSM, and accessible only when several people approve and participate. That makes it extremely hard for a single mistake or insider to compromise the entire hierarchy. Intermediate CAs are usually online, so we compensate with strong network isolation, HSM protection for their keys, and detailed tamper-evident audit logs. If something suspicious happens, you want to see it quickly and prove exactly what was done. The registration authority is all about identity proofing. Here, the control focus shifts to people and process. Background checks on staff, strict procedures, and multi-factor authentication to prevent fraudulent approvals. Repositories and OCSP responders must stay available and honest. They need protection against DDoS, redundancy so clients can always reach them, and integrity checks so revocation and certificate data can't be silently altered. Taken together, these protections defend each component in depth, according to its role and risk, which is what ultimately preserves PKI trust. As PKI grows, the real challenge isn't the cryptography, it's scale. Managing a few hundred or even 1,000 certificates can be done with spreadsheets, tickets, and a single CA server. It's painful, but still manageable. The trouble starts when you reach tens of thousands of certificates. At that point, manual tracking breaks down. Expiry dates get missed, revocation lists grow large, OCSP becomes critical, and every outage turns into a fire drill. This is the tipping point where process and tooling must change. At true enterprise scale, hundreds of thousands or millions of certificates, you need industrialized PKI. Certificates must be requested, approved, issued, and renewed automatically. Protocols like ACME handle renewals. OCSP and repositories are distributed and load balanced globally. You monitor the whole system like any other critical service with real-time dashboards and alerts. The lesson is to design for the scale you're growing into, not the scale you have today. If you wait until you're already at the tipping point, you'll experience outages first and then fix PKI later. At this stage, you already know how PKI should work. Now let's look at how it often fails in deployment. The first big mistake is keeping the root CA online and using it for day-to-day issuance. If that root is ever compromised, your entire trust hierarchy is dead. The safer pattern is to keep the root offline and issue all operational certificates from intermediates. A second common error is standing up a single OCSP server or status endpoint. That becomes a single point of failure. If it goes down, clients can't reliably check revocation, and you're forced into weak fallback behavior. OCSP and status services should be designed with redundancy and load balancing from day one. Third, some teams skip or loosen the registration authority process. If you don't strongly verify identities before issuing certificates, you're building a very expensive impersonation machine. Make identity proofing, approvals, and audit trails non-negotiable. Finally, many organizations neglect revocation data. Out-of-date CRLs or stale OCSP responses mean revoked certificates keep working, which completely undermines your incident response. Automate publication and updates, and monitor freshness just like uptime. All of these are operational choices, not cryptographic ones. Getting them right is what turns a theoretically secure PKI into a trustworthy, resilient system in production. You've seen the moving parts. Now zoom out to what really matters. The root CA is your ultimate trust anchor. It should live offline, be used rarely, and be protected like a crown jewel. Day-to-day work is pushed down to intermediate CAs. They issue most certificates and can be replaced if something goes wrong, without blowing up your entire trust ecosystem. Around them sit the RA, which focuses on checking identities and approvals, the public or internal repositories where certificates and chains are published, and the revocation systems like OCSP and CRLs that act as your policing layer, when keys or identities are no longer safe. Underneath those components are three guiding principles. Distributed trust means you avoid any single point whose compromise would be catastrophic. Separation of duties means the people and systems that verify identities are not the same as those that issue certificates. And scalability means you assume growth, with heavy use of automation, so the system can safely handle many more certificates and services over time. The big idea is this. A strong PKI isn't one big wall. It's a carefully separated chain of trust, where each link has a focused role, and can fail or be replaced, without collapsing the whole system. Let's pull together what you've seen, and stress test it with some what-if thinking. First, treat the root CA as sacred. If that root is ever compromised, every certificate that chains up to it becomes suspect. In practice, that means emergency revocation of the root, pushing new trust anchors to all systems, and often a painful large-scale reissuance of certificates. That's why roots are kept offline and used as little as possible. To reduce that blast radius, you introduce multiple intermediates. Each intermediate can be scoped to a purpose or environment, such as user authentication, servers, or devices. And if one of them is compromised, you only have to replace that segment of the ecosystem, not your entire PKI. For revocation, remember the trade-off between CRLs and OCSP. Severals are useful when you can tolerate some delay, want a simple, cacheable file, or need resilience when online checks might fail. OSSP is better for near real-time status, but it introduces an online dependency and scaling challenge. Scaling OCSP means thinking like an application owner. Use multiple responders, load balancing, caching responses, and short validity periods, so relying parties aren't stuck with stale data. Many organizations also use OCSP stapling to offload checks from the responder to the server presenting the certificate. Now picture a 50,000 employee company. How many CAs would you define? And how would you separate root and intermediates? Which intermediates would you dedicate to internal users, servers, and devices? And where would they live? Online or offline? In which networks or regions? Finally, decide your revocation approach. Will you rely mainly on OCSP with stapling? Keep CRLs as a fallback. And how quickly do you need the ecosystem to react when a key is compromised? Use those questions to sketch a first-pass PKI design. We'll build on this when we look at trust models next.